For decades, quantum physics has been limited by a specific computational bottleneck. To determine how subatomic particles interact, researchers had to calculate infinite probabilities playing out across a sequential timeline. Traditionally, this meant charting every possible path a particle could take through space and time, following each event in a strict chronological sequence. As these interactions scale, the number of potential sequences explodes. Tracking every localized, step-by-step possibility creates a level of complexity that quickly outpaces our strongest processors. In the mid-20th century, Richard Feynman addressed this by developing Feynman diagrams. These tools mapped complex interactions into visual, calculable pathways. Even with these diagrams, calculating a standard scattering amplitude, the probability of particles deflecting off one another, could require hundreds of pages of iterative algebra to account for every possible sequence. This inefficiency is driven by unitarity, a principle that requires probabilities to sum to 1 across a linear timeline. This forces the mathematics into a slow, sequential calculation. However, subatomic reality is far more efficient than the math we use to describe it. It does not pause to run through a sequential timeline, suggesting that our framework for tracking time is a mathematical liability. In 2013, physicist Nima Arkani-Hamed proposed a breakthrough that sidestepped a chronological problem entirely. He suggested that if space and time are not fundamental to reality, they should be removed from the equations of quantum mechanics. His alternative is the Amplituhedra, a static, multidimensional geometric jewel. It encodes the results of subatomic interactions as a single shape. Scattering amplitudes appear as the internal volume of this shape, providing an instantaneous result that replaces traditional simulation. This geometry exists in the positive Grassmannian, a mathematical space where the relationship between points is defined by their position, not by their movement through time. The outcome of an interaction is revealed by the static, measurable boundaries of the shape itself. Arkani-Hamed demonstrated that dynamic execution can be compressed into static volume. If the volume is known, the timeline becomes redundant. To apply this to computer science, researchers are using Lean4, a language built for formal mathematical verification. The goal is to prove that software execution can be mapped to these same geometric principles. This specific repository defines a formal bridge between the discrete logic of a program and the continuous geometry of the positive Grassmannian. The internal documentation explicitly details the golden phase ignition bootstrapping sequence. It uses formal proofs to show that a program's state space is isomorphic to a geometric volume. Instead of running instructions chronologically, the compiler projects the program's constraints into a static coordinate system. This implies that if software can be compiled into a volume, it can bypass the bottlenecks associated with sequential processing. We can see this in action by looking at how the system handles a context-free grammar, or CFG. Traditionally, parsing a CFG involves traversing a tree node by node. This is a sequential process, where each step depends on the one before it. This traversal carries an ON computational cost. The more data there is, the longer it takes to move through the linear sequence. The compile CFG to Grassmannian function intercepts the parsing process before any nodes are traversed. It maps the individual states of the grammar as fixed coordinates in a three-dimensional space and calculates the execution by projecting the constraints onto a solid volume. By treating constraints as volume, the system collapses the ON traversal. The result is calculated through a static projection. This shift from loops to volume addresses the most significant bottleneck in modern artificial intelligence. Modern large language models rely on the transformer architecture and its self-attention mechanism. Self-attention calculates the relationship between every possible pair of tokens in a sequence. This creates a d-squared compute matrix. As sequences grow longer, the number of required pairwise interactions grows quadratically, placing a hardware wall on performance. In a sequential system, this quadratic scaling eventually makes execution impossible within reasonable timeframes. The project repository explicitly asks if geometric volume can replace this d-squared wall. To solve the attention crisis, we must stop processing token interactions step by step and instead find the geometric surface of the data. The first step in Amplituhedra attention is isolating the actual signal. The codebase demonstrates that in many high-dimensional matrices, not every dimension carries relevant data for token interaction. The signal-carrying vectors are identified as standing wave dimensions, represented by the variable k. The mechanism projects queries and keys only into this smaller k-dimensional subspace. This follows a physics principle. Interactions occurring on non-standing dimensions decouple and drop out of the final result. The remaining k by k matrix lifts and folds into a multifaceted polytope in projective space. This is the Amplituhedran vertex. The complexity of pairwise interactions is now mapped to the static boundaries of a minimal shape. This collapse into geometry is defined by a formally verified mathematical proof, the Amplituhedran attention theorem. The theorem replaces a standard softmax calculation across d-squared entries with the evaluation of a scattering amplitude. In this context, the scattering amplitude is an interior point evaluation of the k-squared vertices on the amplituhedran. By utilizing this volume, the O of d-squared attention cost is contained within the O of k-squared compute surface. The math indicates that the attention distribution is already present in the boundaries of the shape, making sequential search unnecessary. The repository defines a specific performance ratio for this reduction. By balancing dimensional factors, specifically the coverage of the standing waves, the system locks in a dimensional partition. When the standing dimensions k represent exactly 1/3 of the total dimensions d, the quadratic interaction space is reduced 9-fold. This 1/3 ratio allows the system to compute the result using only the volume of the isolated subspace. Because the volume is a static property, the processing time does not scale with the sequence length. The framework effectively weaponizes quantum geometry to outpace the limits of classical hardware cycles. This repository demonstrates a transition from chronological computation to volume-based projection. Nima Arkani Hamed's theory, originally focused on subatomic physics, now provides a template for silicon computation. Complex systems no longer require sequential states in time. Instead, the answers are found in the static properties of a multidimensional joule. Treating execution as static volume in the positive Grassmannian removes the dependency on chronological processing, enabling a different approach to artificial intelligence.